Hello everyone, and welcome to video number 3 for Math 235. So in the last video we started talking about limits, and we gave this what we call the intuitive view of limits, this sort of really getting behind the idea of it. And back in the 1600s, when the people who were developing calculus, Newton, Leibniz, etc., were starting to develop calculus. This is the basic idea that they did. But as time went forward, mathematicians started feeling that we needed something with a little bit more humph, a little bit more weight to it, something that was a little bit more precise in terms of how to think about limits. I mean, this is the general view of mathematics. When you say something, you give a statement in mathematics, it should be something that you can clearly verify. And in this intuitive view of limits, it just wasn't quite precise enough to be able to give this clear verification that we want in mathematics. I mean, this is what gives mathematics its power, is that you can say things clearly. So how can we do that with limits? How can we make this a more rigorous definition? So let's go back and let's start with the idea, the intuitive idea that we talked about in the last video. And so it's to say that the limit of f of x as x goes to a equals L. What we're talking about is that as x gets closer and closer to the value a, then the values of the function f of x get closer and closer to the limit value L. Okay. And so we have this idea of closeness here. And so in particular, we have x gets closer and closer to the value a. Well, mathematically, how do you measure how close two numbers are to each other? Right. Well, if we're thinking about close between two numbers, well, that means their difference is small. And really, we don't care whether or not it's positive or negative. And so we're going to look at the absolute value. And so we want this to be small. Now, this is still a little bit wishy-washy at this point, but at least we have an idea of this is what we mean by closeness. We're talking about the absolute value of the difference between these two being small. Right, so we have the absolute value of x minus a is small. Similarly, we want f of x to be getting close to L. Well, same as before, how do we measure how close f of x is to L? Well, we're going to take the difference between f of x and L, take its absolute value, and then see if that is quote-unquote small. Okay. So, really, what we're saying in this definition is that if the absolute value of f of x, we need that the absolute value of f of x minus L to be small when the absolute value of x minus a is small enough. So f of x is close to L. The absolute value of f of x minus L is small when x minus a, when x is close to a. So when the absolute value of x minus a is small enough. So this is how we precisely say that. I'm just going to put it up there and then we'll talk through it. Okay. So this is our rigorous definition of a limit. Let epsilon greater than 0 be small if there exists a small delta greater than 0, such that when x minus alpha, take its absolute value, is less than delta, we have that f of x minus L, its absolute value, is less than epsilon. That's what we precisely mean for the limit of f of x to equal L as x goes to a. Okay, so let's piece through. So we're adding in these two variables here. One variable, epsilon, and so epsilon, this is tying into how close f of x is to L. Okay. And so the idea is, let me frame this back the other way. I'm going to claim that the limit of f of x is, as x goes to a, is equal to L. Okay. And the way I'm going to do that is I'm going to say, okay, you pick any small positive number you want. I'm going to call that small positive number epsilon. If I can find some distance that I need to keep x close enough to a, such that we always land, f of x always lands within epsilon of L, that's when we're going to say we have the limit. So let's put this into a picture. Okay, so here's the definition on top, and here's a function, and I think we can agree that whatever the definition of limit should be, that it should work for this picture here, that this picture, in this picture, as x goes to a, the limit of f of x should be L. Okay, so this is what the definition says. So first we're going to pick our epsilon. Now epsilon is talking about how far the distance between f of x and L. Right? So if the absolute value of f of x minus L is less than epsilon, this is the same thing as saying if I drop the absolute value, that f of x minus L, it has to be less than epsilon, but it also has to be bigger than minus epsilon. If it's between minus epsilon and epsilon, then f of x is close to L then. Okay? And then if I add L all the way across here, what this means is that the values of my function have to be between L minus epsilon and L plus epsilon. Okay. Now, since this is talking about f of x, L and L is a y value, f of x is a y value, we're both talking about L minus epsilon and L plus epsilon as being around L on the y-axis. Okay, let's drop those in. So there's L plus epsilon, and then there's L minus epsilon. Okay, now we're looking for an area such that f of x stays between these two bounds. Okay, so let's draw horizontal lines out across from L plus epsilon and L minus epsilon. There we are. And as you see, there's a space around A where the function stays between these two red lines. And in fact, I can pick some little distance out. So I can go a little distance this way, same little distance this way. And if I go between these two lines, let's make this a little bit prettier. Oh, now we have these nice magenta colored lines. If you look, if I take any x value between these two magenta lines, the value of the function between this stays between the two red lines. Okay. So for all x values between the two magenta lines, the values of the function, the blue part, is in between the two red lines. Now another way that we kind of think about this, as you can see, we have this nice box that we've created. And in this box, the function is allowed to go out the sides of the box, but not the top or the bottom. Okay, because between these two left and right sides, the function has to stay below the top and above the bottom. That's the L plus epsilon and the L minus epsilon. If the function is staying between those two while it's inside the box, that means we have kept the values of the function close to L all the way across. And so then this distance between A on either side, this distance between A and right there, that is our delta. Okay. So we started off with the epsilon. From the epsilon, we went up from L and down from L, created these red lines. And then once we had these red lines, we then were able to find these vertical lines going around A, such that the value of the function stayed between the two L plus epsilon and L minus epsilon between these two lines. And then the distance away from A of these lines, that's our delta. Okay. And so to be clear, for all the x values where the absolute value of x minus a is less than delta, right? And so same as the other way, x minus a being less than delta, that's the same thing as saying x is less than delta and bigger than minus delta. And so what are the values for x? It's between a plus delta and a minus delta. This magenta line is a minus delta. This magenta line is at a plus delta. Okay, so let's try and make this tangible with a tangible example. We're actually picking values for epsilon and finding a value for delta. Okay, so example, we're going to start with real simple function, just the line 3x minus 5. And so the question is, how close does x have to be to 2 for f of x minus 1, an absolute value, to be less than 0.5? So what's playing the role of epsilon here? Well, since it's on the other side of the absolute value, this is our epsilon. Okay. What's playing the role of a here? Well, a is talking about the x value that we're approaching. So 2 is playing the role of a. And what's playing the role of our limit? Well, we're measuring how far f of x is from 1. So 1 is our limit. Okay. And so when the question is how close does x have to be to 2, the question is asking, what does delta have to be? Okay, so let's clear this out and start working it out. Okay, now we have some space. Okay, so f of x, that's 3x minus 5 minus 1. Now we want this absolute value to be less than 0.5. And so if we want the absolute value to be less than 0.5, that means we want it to be less than 0.5. And we also want it to be bigger than minus 0.5. When it's in between these two values, then its absolute value is less than 0.5. Okay, now we're just going to start doing some algebra. So over here I've got 3x minus 6, simplifying on the inside. Okay, now we're trying to measure how close x is to 2, and so that's going to be talking about the absolute value of x minus 2. Well, look at 3x minus 6. I can pull a 3 out of this, and I'm left with x minus 2. Right. And then I want x minus 2 by itself, and so I can divide by 3 on each side. And so x minus 2 less than a half divided by 3, that's less than a sixth. And then on the other side, I'll be less than minus a sixth. Okay. And so then when x minus 2 is between a sixth and minus a sixth, then 3x minus 5 is going to be within a half of 1. Right. So we have figured out that the absolute value of x minus 2 has to be less than 1/6. This 1/6 here, that is our delta. So when the absolute value of x minus 2 is less than 1/6, then the absolute value of f of x minus 1 will be less than 1/2. So what if we change our epsilon? So now the epsilon, we've shortened it down to 0.01. Now this is a different number, but the idea is the same. And so we're going to go through the same way. So for f of x, I'm going to plug in 3x minus 5 again, subtract off 1, but now we want it to be between 0.01 and minus 0.01. But we can do the exact same thing we did before. This turns into 3x minus 6 between 0.01 and minus 0.01. we can pull out the 3 and divide it out. And we're going to have x minus 6 is less than, so 0.01 is 1/100th divided by 3 gives me 1/300th. On the other side, I had to have minus 1/300th. And that should not be 6. That should be a 2 there. All better. And so if the distance between x and 2 is less than 1/300th, then the distance between f of x and 1 is going to be less than 1/100th. Okay, and so for the epsilon equal to 0.01, our delta is going to be 1/300. So let's do one more, but rather than plugging in an actual value for epsilon, let's leave epsilon as a variable. We're just thinking about epsilon as being some small positive number. So again, the idea is if you give me a small positive number, as we've done in the previous 2 examples, I then can find a delta that works. Okay, so now we're just gonna prove it, show it for any epsilon you would give me, how I would pick that delta. So, and the work is exactly the same as before. We have 3x minus 5 minus 1 is less than epsilon, bigger than minus epsilon, turns into 3x minus 6 between epsilon and minus epsilon. And so then pull out a 3. 3 times x minus 2 is between epsilon and minus epsilon. Divide by 3. I'm going to get that I need the absolute value of x minus 2 to be less than epsilon over 3. So a delta that works, a delta that's always going to work, is no matter what you give me for epsilon, I'm going to take that, divide by 3, and say that's how close x has to be to 2. Okay, and so in general, this is how these problems are going to work out. At the end, when you're doing this in terms of epsilon, your answer for delta will depend on epsilon. If you change what epsilon is, it's going to change what delta is. And so really, delta will be a function of epsilon. Okay. So if we kept on going and you said if you wanted to make epsilon equal to, say, 1/1,000,000th, you said, oh, try and find that value now. Well, now I know that whatever epsilon you give me, I'm just going to divide it by 3, and that's going to be the right delta. And so if you set epsilon to be 1/1,000,000, then I'm going to set delta to be 1/3,000,000. And we're in good shape. Okay, so we also looked at some infinite limits in the last video. So let's talk about how we need to adjust this definition to fit infinite limits. So as you recall, for our definition for infinite limits is if as x goes to a, all the values of f of x get bigger and bigger with no upper bound. That's what we mean when we say f of x, the limit as x goes to a of f of x equals infinity. Well, so we want f of x to be getting bigger and bigger and bigger. So how can we measure that? Well, so what we're going to do is we're going to pick some big M, some big number M, and just say, okay, if f of x is big, then it should be bigger than this big number M. Okay, and so that's how we're going to measure the bigness of f. If the values of f are bigger than M, then we're saying it's big. Okay, and so the idea of closeness for between x and a is going to stay the same. And so our new definition is let M be big. And so this is sort of an analog of epsilon being small. Now to go off to infinity, we want M to be big. then there exists a small delta greater than 0, such that when x minus a is less than delta, so when x is close enough to a, which we measure using delta, then we have that f of x is bigger than m. So f of x is big. It's bigger than our big number m. That's what we're saying when the limit, that's what we mean when we say the limit of f of x as x goes to a equals infinity. Okay, so let's go through this in the same way as we did with the last one, showing this what we mean by this in a picture. So here's our definition again, and here's a picture of a function. And I think looking at this, we can agree that whatever the definition should be, it should be showing for this picture that the limit as x goes to a of the function should be going off to infinity, right? So this is a function that should be going off to infinity. So let's make sure it works. Okay, now the definition says first pick m to be a big number. So let's pick a big number m and let's put it down on the y-axis. Okay, so there's our big number m. Okay, now we want to end up with our function being bigger than m, the values of our function to be bigger than m. So let's draw a line across from m. And then as we draw this line across from m, you can see that it gets to a point, once we get close enough to a, that the values of the function go above this line. So once we are close enough to a, all the values of the function are up above the red line here, right? So close enough to a, we're going to pick some little distance out from a, and then from there, we're going to draw straight lines up. And in between these two vertical lines, all the values of the function are above the red line. So the picture here, maybe everything's a little bit too close together. This is what happens as things go off to infinity. So let's zoom in a little bit right there. And as you zoom in, so this is zooming in right to where all the action is happening, you can see, same as before, we have this sort of box that we've made. And between the magenta lines, all the values of the function, all these values here are bigger than the red line m. So once we got close enough in, then all the values of the function end up being above this line. Now, what happens if we made, say, m bigger? So instead we cut across here. Could we still find something that works? Sure, we're just going to have to make it smaller. Right? So the idea here is that as m gets bigger, the delta will have to get smaller. Okay. But no matter how big you make m, I can find some delta small enough that makes this work. Okay, so there's one more type of limits that we didn't talk in the last video, so let's start talking about them now. And so these, instead of the values of our function going off to infinity, we're thinking about functions that go to a limit as x goes off to plus or minus infinity. So when the values of the function were going off to infinity, we were talking about vertical asymptotes. Well, now if we're letting x go off to infinity and the function going to a value, now we're talking about horizontal asymptotes. So this is essentially what we mean, right? So we have this function in blue as we go out further to the right. So as x is going off to infinity, that means we're looking at the function as it moves to the right. It's getting closer and closer to this red line at L. Okay. Now in this one, we have it moving very nicely towards the red line. It doesn't have to do that. In fact, it could bounce all the way around. And so here's a little bit of a funkier one, bouncing all around. And you can see that it's hitting L and going away from it, but then afterwards, all the values are getting closer and closer to L. So on the left, we see that the crests are getting further away from the line than they do on the right. So as we go further to the right, all the crests, all the values of the function are staying closer and closer to the line. Okay. So in this case, we would say the limit as x goes to infinity of f of x equals L. And so intuitively what that's saying is that as x gets bigger and bigger, the values of the function get closer and closer to L. Well, how are we going to make this definition more rigorous as we've done in the other ones? So now we have f of x getting closer to L. So same as before, we can use an epsilon for that. But now we're talking about x getting bigger rather than f of x getting bigger. Okay. So again, the key part of the definition is x gets bigger, the values of f of x get closer to L. So here's our definition. So since we want f of x to get close to L, we're going to use epsilon to measure that distance. So let epsilon be small. If there exists a large n, so this n we're going to use to measure x, such that when x is larger than n, we have the distance between f of x and L is less than epsilon. That's what we mean when we say that the limit as x goes to infinity of f of x equals L. So let's plug this back into our picture. Okay, so here's our L, here's our function that as x goes out to the right, all the values are getting closer and closer to L. Okay, now first we're picking an epsilon. So same as before, we're going to look at L plus epsilon and L minus epsilon, and we're taking lines going out from there. Now as you go out, you can see early on, there may be some values that are between, and then it starts bulging out. But then as we go further right, it stops going in and out of those green lines. And there gets to be a point where the rest of the way, it's in between those two green lines going across. Right? So once that happens, and so we can pick a point after that happens, we're going to call that n. And then if you look to the right of n, the function now between those stays between the top and the bottom. So same as before, once we get into our region, so our region starts at n, inside of here, the function is staying below the top and above the bottom. It's staying in between the two values. And so that's what we mean when we say that the limit of f of x as x goes to infinity equals L. That is all for this video. I will see you again soon.